Hello, for today's video lecture we're going to be talking about structures. So in engineering, a structure is any collection of connected bodies. So we can look at something like a pair of scissors here, and here we've got three different bodies. We've got kind of the back blade and handle, the front blade and handle, and they're held together with a rivet. So here we've got three different bodies. They are all connected together. This would be an example of a structure. We've got something like a bridge. This is more traditionally thought of as a structure. So the bridge has many different components, many different bodies that are all connected together into a cohesive whole. In this case, the bridge is rigid, unlike the scissors, but this is still going to be a structure. Finally, we've got something like a stool over here. So this is a structure that's clearly in 3D. So I could treat this as one single body. I could just talk about the stool and analyze the stool as a whole, but I could also treat this like a structure. So the stool has many different parts that are all connected together, and I might want to analyze individual parts. Alright, so next up we want to talk about types of structures. And so this is going to be really important because the type of structure is going to influence what we do to analyze the structure and determine the forces acting on the pieces. So first up, we've got a truss. A truss is a rigid assembly made entirely of two force members. And later on, we're going to talk more about what a two-force member is. We've also got a frame, which is a rigid assembly containing at least one member that's not a two-force member. And we've got a machine, which is a non-rigid assembly containing at least one member that is not a two-force member. So the big distinction right here is going to be with the distinction between truss and not a truss, or truss and frame and machine. Because we have one method for, or we have a couple methods for trusses, and we've got other methods we are going to use for frames and machines. Alright, so the basic analysis process either way is going to be the following. So as with everything in statics, the structure is assumed to be in equilibrium. That means that the sum of the forces must be equal to 0 and the sum of the moments must be equal to 0. Because the structure is in equilibrium, each member or part of the structure is also going to be in equilibrium. So for each piece, member AB, like we have up here, and member BC down here, for this, the sum of the forces must be equal to 0 and the sum of the moments must be equal to 0. And same thing for member BC down here, the sum of the forces must be equal to 0 and the sum of the moments must be equal to 0. So we analyze structures by breaking them down into parts and then performing static analysis on each of the pieces. Alright, so when making the jump from analyzing a single body to analyzing a collection of bodies, or a structure, there are two important factors we want to talk about. Number one is the application of Newton's third law, and number two is the identification of these two force members. So let's go into a little bit of depth on each of these pieces. So Newton's third law, as a review, states that for every action or force, there's an equal and opposite force that exists. So in a structure, this means whenever two bodies are connected, the force that body A exerts on body B will be equal and opposite to the force that body B exerts on body A. So here we've got a clamp on a table, and we've got actually two of these Newton's third law pairs. So the contact point at the top, we'd have a normal force going up on the clamp and a normal force going down on the board. And then down here at the bottom, we have another Newton's third law pair. We have a force from the clamp onto the board going up, a force from the board going down on the clamp. So this is a set of equal and opposite forces. This is a set of equal and opposite forces. Anywhere you've got a contact point between two bodies, you're going to have this Newton's third law pair. And so here in our structure, we can actually see one of these Newton's third law pairs in our free body diagrams. So though we analyze each body separately, the third law pairs exist whenever we've got the connection point between two of the pieces. And here at point B, we've got our connection point. So member AB is connected to member BC. And so the force at B here is going to be equal and opposite to the force at B over here. So this is the force on member AB, this is the force on member BC, equal and opposite. And they're always going to be equal in magnitude, opposite in direction, so if we figure out one of them, we're going to know the other. And this has the effect of reducing the number of unknowns you need to solve for in the overall problem, because if you solve for FB once, then you know it's a known value going into the analysis of the second piece. All right, next up we have two force members. So a two-force member is a body that has forces and no moments exerted at only 2 points. So if we've got two connection points, like we have in both of them, so A and B, we've got pin joints, possibly forces at each of those pin joints, same with BC. But we have a force in the middle of BC. So I've got forces at 1, 2, 3 points down here. This is not a two-force member. I've got forces at 1, 2 points up here. This one right here is a two-force member. And a two-force member will have two equal, opposite, and collinear forces acting on it. So it's going to look like this. It's either going to be in tension or compression. On the following page, when we talk about two-force members, we're going to go into a lot more depth about why that must be true. But for now, we know that it's either tension or compression. And this is as a result of Newton's second law. So this is also going to reduce the number of unknowns that we need to solve for, because it's equal and opposite, just like our Newton's third law pairs. And if I solve for the force on one end, I'm going to know the force on the other end. And also, right off the bat, it's a known direction. So it's going to be acting along this line of the member. So overall, methods for analyzing structures. We first want to identify the type of structure that you have. For trusses, we're going to have something called the method of joints, the method of sections, or we can kind of have a hybrid method of joints and method of sections. For frames and machines, we've got a separate analysis method, so there's no real title for this method, it's just the analysis of frames and machines. And it's going to rely heavily on Newton's third law, and it's still going to be important to identify the two force members for this as well. So just like we talked about earlier, there's two important pieces in all structures are going to be important for frames and machines. All right, that's all we have for today's video lecture. Thank you for watching, and I hope to see you again.